Between November 5th and December 3rd, 2025, something changed in the way 3i Atlas responded to measurement. The astrometric track, positions measured against background stars, began showing residuals that had not been there before. Small deviations, fractions of an arcsecond, the kind of drift that suggests a force beyond gravity is acting on the nucleus, nudging it slightly off the trajectory that pure celestial mechanics would predict. By early November, the non-gravitational acceleration term had appeared in the orbital fits at 3.7 standard deviations. Not overwhelming, not definitive, but present, and mathematically coherent. The radial component pushed outward from the Sun at 1.1 times 10 to the -6 astronomical units per day squared. The transverse component acted perpendicular, 3.7 times 10 to the -7. These are the signatures of an object responding to something: solar heating, outgassing, radiation pressure, or a mechanism not yet identified. But when you looked at the images, you saw nothing to explain it. No dramatic brightening surge beyond what perihelion geometry would predict. No obvious extended coma leaping out of the data. Broadband photometry from multiple observatories showed mostly stable color evolution through the period. The G-band magnitude varied gently with a 16-hour periodicity consistent with rotation, not chaos. The object looked calm, controlled, unremarkable in the optical bands where comets usually announce their activity. Researchers began to split into interpretive camps. Some trusted the orbit fit, arguing that astrometry, when done carefully across many observatories, is one of the most robust measurements in astronomy. Others trusted the photometry, pointing out that if the object were truly shedding mass fast enough to produce that acceleration, you should see it. You should see gas, dust, extended structure, a tail, something. The question that opens this investigation is not what 3i Atlas is doing. The question is what we failed to measure while it was doing it. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. The expected signal, when absent, can be more informative than a detection. It tells you where to look, what to suspect, what assumptions might be failing. For a comet showing non-gravitational acceleration near perihelion, which 3 Atlas reached on October 30th at 136 astronomical units, there's a standard checklist of observable consequences. Even weak outgassing episodes leave fingerprints. Gas emission lines in the near-infrared. Broadband color shifts as the dust-to-gas ratio changes. Asymmetry in the coma, especially downwind of active vents. Temporal variability in brightness that correlates with distance from the Sun, not just rotation. And if the mass loss is large, if the object is shedding 13% of its total mass, as momentum conservation would require to produce that acceleration with thermal speed molecules, then the coma should be massive, obvious, impossible to miss. But through late October and early November, while the object was inaccessible from Earth due to low solar elongation, spacecraft observations told a different story. NASA's Parker Solar Probe watched 3i Atlas from October 18th through November 5th with its wide-field imager. The comet appeared faint, compact, not obviously erupting. When ground-based telescopes regained access in mid-November, photometric monitoring resumed. Observations from Gemini North on November 26th, using the GMO-IS instrument, captured the comet with a faint greenish glow. Evidence of diatomic carbon emission, likely from carbon-carbon emission, likely from carbon-carbon or cyanogen molecules fluorescing in sunlight. Green is good. Green means gas, torch. But the emission was faint. Subtle, not the blazing coma that 13% mass loss would produce. Spectroscopy provides the cleanest constraints. If gas is present, spectroscopy sees it. If gas is absent, spectroscopy sets limits. Observations through late November and early December revealed something unexpected. The coma was not absent. It was simply not dominated by water. Very large telescope spectroscopy detected nickel and cyanogen onset, neutral nickel atoms at specific wavelengths, CN radicals fluorescing in the violet and blue. But water emission remained weak. Earlier infrared observations from the James Webb Space Telescope in August had shown a carbon dioxide-rich coma with only 4% water by mass. That ratio is extreme. Most solar system comets are water-dominated. Borisov, the previous interstellar comet, behaved like a typical water ice body, but 3I Atlas does not. And if the dominant volatile is carbon dioxide instead of water, then the thermal velocities, and thus the momentum budget, change. Co-molecules at the same temperature move slower than H and EO. To produce the same thrust, you need more mass loss, or you need something else contributing to the acceleration. The investigation turns clinical. How sensitive were the observations? What could hide beneath the detection limits? A compact, low-contrast coma aligned along the line of sight might be effectively invisible in projection, even if substantial in 3 dimensions. Dust thermal emission in the mid-infrared would be faint at 1/4 astronomical units, unless the grains were very small and very hot. Imaging cadence matters. If the activity is episodic, occurring in bursts separated by quiescent periods, then sparse sampling could miss the active phases entirely and catch only the aftermath. The NASA Sphere-X spacecraft reobserved 3 Atlas in December, post-perihelion, and found the object markedly more active than in August. Gas emission from CN, water, organic, carbon-hydrogen bands, KOMU, and CO, were all detected. The carbon dioxide coma remained spatially extended out to at least 3 arc-minutes radius, roughly 348,000 kilometers. A weak, pear-shaped dust tail, consistent with large grains, had developed, pointing generally sunward at certain viewing angles, which is geometrically unusual and suggests radiation pressure effects or rotation-induced asymmetry. So the gas was there. The dust was there. The activity was real. But it did not match the timing, the intensity, or the spectral signature that the astrometric residuals seem to demand. And that mismatch between what the orbit says happened and what the images say happened becomes the central tension. We may have stared directly at the object in multiple wavelengths with sensitive instruments while missing the channel where it was speaking most clearly. There are 2 truths, and they do not collapse into one. The first truth lives in the orbit fits. When you take the astrometric data from over 200 observatories spanning May through December, you can fit a purely gravitational trajectory. The fit is decent. The residuals are small but patterned. They show structure, not random scatter. Alternatively, you can fit a model that includes non-gravitational terms. 2 parameters. Radial and transverse acceleration scaled to decrease with the square of heliocentric distance, mimicking solar heating. That fit is statistically better. The residuals shrink. The patterns weaken. The improvement is not dramatic, but it is measurable. And because the non-gravitational terms are physically plausible, they match the functional form expected from cometary outgassing. The model feels justified. The second truth lives in the light curve. Photometric monitoring from multiple sites shows that 3I Atlas has a rotation period near 16.6 hours, derived from periodic brightness variations. The amplitude is modest. The shape is relatively smooth, consistent with an elongated or irregular nucleus tumbling in space, presenting different cross-sections to the Sun, an observer, as it rotates. Crucially, the light curve does not show the chaotic, spiky variability you would expect from a surface suddenly venting gas in large, asymmetric bursts. It shows rotation. Steady. Predictable. The kind of signal that makes you think the nucleus is structurally intact, not fragmenting, not violently active. So, here's the contradiction. The orbit says, something pushed this object starting near perihelion. The photometry says, the object's appearance remained rotationally modulated and relatively stable. Both datasets are careful. Both are reduced by professionals. Both are published. And they do not agree on what the object was doing. The methodological move now is to ask, what systematic effects could create apparent acceleration without real thrust, or real thrust without visible activity? Star catalog biases can introduce false positional trends, if the reference stars themselves have unmodeled proper motions or incorrect parallaxes. Atmospheric refraction near the horizon bends light predictably, but if the refraction model is slightly wrong, or if the temperature and pressure inputs are inaccurate, the astrometry shifts. Timing offsets, if the observation timestamps are recorded at the start of the exposure instead of the midpoint, or if the clocks are not synchronized across observatories, can create apparent motion that is not real. Filtered differences matter because comet comae are not uniform in color. The photocenter in the blue may not coincide with the photocenter in the red, so measuring positions through different filters can introduce small, systematic shifts. None of these effects are large, but they do not need to be large. The non-gravitational acceleration being discussed is tiny, less than 1 part in 10 million of the gravitational acceleration at Earth's surface. Systematic errors at the sub-arcsecond level, compounded over months, can mimic or erase signals of that magnitude. And yet, the residuals look too structured to be pure noise. They cluster. They drift coherently. They feel like something real trying to emerge from the data. The mystery advances because neither interpretation collapses. The orbital signal persists. The photometric calm persists. And the gap between them remains unexplained. Geometry is not just background. It is an active player in this story. Phase angle, the Sun object observer angle, shifts continuously as the object moves and as Earth moves. At small phase angles near opposition, the object appears bright because backscattering dominates. Light bounces directly back toward the source. At large phase angles near conjunction, forward scattering takes over, and brightness drops steeply. For an irregular, porous surface covered in fine dust, phase angle effects can be extreme. A factor of 2 change in brightness over 10 degrees of phase angle is not unusual. If the orbital solution places the object at a slightly different position than reality, then the inferred phase angle is wrong, and the brightness correction is wrong, and what looks like a brightening surge might just be geometry. There is another subtlety. A rotating body presents different facets to the Sun and observer over time. If the nucleus is elongated, or if one hemisphere is darker than the other, then the projected cross-section and average surface brightness change with rotation. Viewing aspect, the angle between the rotation axis and the line of sight, determines how much of that variation you see. If the rotation axis happens to point nearly toward Earth, you see the object nearly pole on and rotational modulation becomes weak. If the axis is in the plane of the sky, you see the object equator on, and modulation becomes strong. The 16-hour period suggests the latter. But if the axis precesses, or if the observations span a geometry transition, the light curve shape can evolve in ways that mimic activity. Dust scattering adds complexity. A compact coma, gas and fine dust, extending only a few thousand kilometers from the nucleus, can be optically thick enough to brighten the object significantly while remaining spatially unresolved in ground-based images. If that coma is illuminated at a favorable phase angle, it scatters efficiently. If the phase angle shifts, the scattering efficiency drops and the coma seems to vanish. It has not vanished. It is simply no longer backlit. The investigation reframes. What if the missing coma is not missing but just hard to see? What if the gas is there, below spectroscopic detection limits, and the acceleration is real, but the geometry conspired to hide the evidence precisely when we were looking hardest? The question tightens. What observation would be immune to geometric tricks? What measurement could discriminate between apparent change and real change? The answer is polarization. Dust scattering polarizes light in ways that depend on grain size, composition, and scattering angle, not on brightness alone. A polarimetric survey of 3I Atlas would reveal whether the light is coming from bare nucleus or from dust-laden gas, regardless of how faint the coma appears. But polarimetry is expensive, time-intensive, and by the time the need became clear, the object was already receding. Timeline becomes the next investigative layer. When did things happen? The answer depends on which dataset you trust. Astrometric fits place perihelion at October 30th, 2025, at 4 hours 21 minutes at ECTC. The uncertainty is minutes, not hours. But when did the non-gravitational acceleration begin? The pre-perihelion data, spanning May through September, showed no significant acceleration. Upper limits were tight. The object moved on a purely gravitational path. Then came the observational gap. From late September through mid-November, the comet was too close to the sun in the sky to observe safely from Earth. Solar elongation dropped below 30 degrees. Twilight interference. Scattered light. Observing windows closed. During that gap, perihelion occurred. During that gap, the object's heliocentric distance dropped to its minimum. Solar heating peaked. And, if the standard cometary model is correct, outgassing should have surged. But we were not watching. Spacecraft were watching, but spacecraft see different wavelengths, different spatial scales, different sensitivities. When ground-based observations resumed in mid-November, the astrometry already showed residuals. The acceleration term was already needed to fit the orbit. So the push either began during the gap, or it began earlier and was masked by insufficient data. If it began during the gap, then cause and effect align nicely: peak heating, peak outgassing, peak thrust. If it began earlier, then something else triggered it, something not directly tied to heliocentric distance. A delayed thermal response. Subsurface ice layers that took weeks to heat through. A rotational orientation that brought a previously dormant vent into sunlight. Or a transient event, an impact, a fracture, a landslide that released buried volatiles independent of solar distance. Photometry provides another timeline. The rapid brightening reported in the weeks before perihelion, rising by a factor of 5 in green band magnitude between early October and late October, suggests surging activity. But that brightening was observed when the comet was at large phase angles and low solar elongations, meaning the geometric corrections are large and model dependent. When the object reappeared in late November, its brightness had stabilized. The light curve was smooth, rotational, not eruptive. So either the brightening was a transient event that ended, or it was a geometric artifact that never happened. And if it never happened, then the acceleration inferred from astrometry becomes even harder to explain because there is no matching photometric response at all. The dissonance sharpens. The dynamical data says the object accelerated. The optical data says the object stayed calm. The spectroscopic data says gas is present, but not water-dominated. The infrared data says carbon dioxide is abundant and spatially extended. The X-ray data. Yes, there is X-ray data. The XMM Newton Space Telescope detected soft X-ray emission from 3I Atlas in early December, extending out over 250,000 kilometers. Says the coma is interacting with the solar wind, ionizing gas, producing charge exchange signatures. Every measurement is real. Every measurement is carefully done, and they do not tell the same story. When timing breaks, when cause does not precede effect in the expected order, our instincts about causality become the least reliable instrument we have. We assume that solar heating drives outgassing, that outgassing produces thrust, that thrust alters the orbit, and that these steps happen in sequence. But if thermal inertia is high, the sequence blurs. If volatile reservoirs are localized and rotation-dependent, the sequence becomes episodic. If the mechanism is not outgassing at all, the sequence is wrong from the start. The environment matters. We ask what the object is doing, but we should also ask what it is moving through. The solar wind is not uniform. It is structured, gusty, variable. Coronal mass ejections, huge eruptions of plasma from the sun, sweep through the inner heliosphere, compressing and disturbing the ambient wind. The heliospheric current sheet, the boundary where the solar magnetic field flips polarity, ripples, and warps. Plasma density and velocity change on timescales of hours. For a comet near 144 astronomical units, these changes are not academic. Radiation pressure from sunlight scales with the inverse square of distance and can dominate the dynamics of small dust grains. For particles smaller than a micron, radiation pressure is stronger than gravity. Those particles accelerate outward, potentially faster than the bulk gas flow. creating a diffuse dust halo that is hard to detect but dynamically important. There is a scenario, cautious, model-dependent, not widely accepted, that a very small dust population below the detection threshold of visible light imaging could experience enough radiation pressure to alter the photocenter of the object as seen by astrometric telescopes. If the photocenter shifts, the measured position shifts, and the orbit fit interprets that as motion. The object did not move. The light distribution moved. The acceleration is an optical illusion, but this requires the dust to be both abundant enough to shift the photocenter measurably and diffuse enough to avoid detection in images. That is a narrow window. Most researchers consider it unlikely. Yet it remains on the table because it would reconcile motion with silence, apparent thrust with no visible coma. Plasma interactions at another layer. If the coma contains ions, charged atoms and molecules produced by ultraviolet sunlight ionizing neutral gas, those ions feel the solar wind as a force. They are picked up by the wind, dragged outward, forming an ion tail. For typical comets, the ion tail is long, narrow, and blue-tinted from carbon monoxide plus and other molecular ions. For 3 Atlas, ion tail detections have been sparse and ambiguous. Some images show faint extended structure, others show nothing. If the ion production rate is low, if the coma is Cu-rich, but HEO poor, and if Cu ionizes less efficiently, then the ion tail would be faint. And a faint ion tail might exert drag forces on the nucleus that are small, but non-zero. Enough to contribute to the residuals. Not enough to explain them entirely. The mystery advances because the environment provides new explanatory pathways while preserving uncertainty. Nothing here is definitive. Everything is plausible. Cadence gaps are literal blind spots. Astronomy happens on clear nights, at dark sites, when the object is above the horizon and not too close to the moon. Those conditions do not align continuously. For 3I, Atlas, the July discovery was followed by intensive monitoring through August and early September. Then, solar elongation dropped. Observations thinned. The critical perihelion window, late October through early November, was largely unobservable from the ground. Spacecraft helped. Parker Solar Probe, Europa Clipper, Spherix, Maven at Mars, Hubble, when the object was far enough from the Sun. But spacecraft have their own cadences, their own sensitivities, their own blind spots. Spherix observed in August, then again in December. A 4-month gap. Anything could have happened in between. Small events can hide in gaps. A brief outburst lasting hours would be missed if no one was watching. Large events can be mischaracterized if you only catch the beginning or the end. If the object brightened sharply on October 28th, stayed bright for a day, then faded by October 30th, and your next observation was November 2nd, you might infer a gradual rise and fall when the reality was a spike. Light curve sampling becomes critical. If you observe once per night, you see daily averages. If the object has a 16-hour rotation period, you are undersampling. The rotation aliases into longer timescales, and you might mistake rotational modulation for secular trends. Processing pipelines introduce their own blindness. Modern astrometric software automatically identifies and removes cosmic rays, hot pixels, satellite trails, and faint streaks that might be asteroids. But a faint, extended coma can look like background noise to an algorithm trained to find point sources. It gets subtracted. Erased. The final image shows a clean, sharp nucleus because the pipeline was too good at its job. Human inspection catches some of these cases, but not all. And if the coma is only marginally extended, just barely resolved, just barely above the background, then whether it survives processing depends on parameter choices made months earlier, when no one knew 3 Atlas would be unusual. Field crowding matters. Some regions of the sky are dense with stars. If the comet passed through a crowded field, then background star contamination makes photometry harder and astrometry noisier. Observers avoid crowded fields when possible. But comets do not care about observing strategy. They go where their orbits take them. And if a critical observation was postponed because the field was too crowded, and the weather turned bad the next night, and by the time the sky cleared the geometry had changed, those gaps accumulate. Sometimes the missing piece is not physics. It is a scheduling decision made in June that cascaded into a gap in November. The discipline of not knowing is harder than it sounds. There is pressure to conclude, to declare the object natural or anomalous, active or dormant, understood or mysterious. But the data does not support any of those conclusions cleanly. The remaining tension is real and unresolved, a dynamical hint of forcing present in the astrometric residuals at modest statistical significance, an optical appearance that refuses to show dramatic corresponding activity in the wavelengths looked, and multiple ordinary explanations that each fit only part of the record. Carbon dioxide outgassing could explain the spectroscopy and the infrared coma, but requires mass loss that should be more visible. Geometric effects could explain the photometric stability but do not explain the residuals. Systematic astrometric errors could explain the residuals, but only if multiple independent observatories made correlated mistakes in the same direction. Radiation pressure on dust could shift the photocenter, but requires a dust population that imaging does not confirm. Plasma interactions could provide additional forces, but are too weak to dominate at this distance. What would genuinely discriminate? A coordinated multi-wavelength campaign with guaranteed cadence. Photometry every night in multiple filters to fully sample the rotation period and catch transient events. Spectroscopy at high resolution to measure gas velocities and composition unambiguously. Polarimetry to constrain dust properties and detect faint coma regardless of brightness. Astrometry from space-based platforms to eliminate atmospheric refraction and achieve sub-millisecond precision. Infrared monitoring to track thermal emission and dust production continuously. And all of it simultaneous, so that you can correlate positional residuals with photometric changes, spectroscopic detections with brightness spikes, and geometry with apparent behavior. That campaign did not happen. Could not happen. The object was discovered too late, moved too fast, and was too faint for the necessary coordination. The opportunity passed. We are left with fragments. Observations scattered across wavelengths, instruments, observing windows. Each fragment is valid within its own context. Together, they do not assemble into a single coherent picture. That is not failure. That is the reality of observing interstellar visitors, rare, fast, arriving on schedules that do not align with human readiness. 3I. Atlas is the third confirmed object from beyond. The sample size is 3. We cannot yet say what is normal for interstellar comets because we do not know what normal looks like. Oumuamua showed no coma, no gas, and bizarre non-gravitational acceleration. Toy Borisov looked like a solar system comet, water-rich, well-behaved, unremarkable. 3 Atlas sits somewhere between. Gas present but not water-dominated. Acceleration measured but not confidently explained. Appearance calm but spectroscopy strange. The universe often reveals itself not through certainty, but through the parts we have not learned to see yet. 3 Atlas is receding now, beyond 2 astronomical units from Earth, dimming steadily, moving at 58 kilometers per second relative to the Sun. By mid-2026, it will be too faint for most telescopes. The data archive will close. What we have now is what we will always have. And within that archive, there is a pattern, or the suggestion of one, that refuses to resolve. The object may have accelerated. The object may have remained inert, and we misinterpreted noise. Both are possible. Both fit subsets of the evidence. And the honest conclusion is that we do not know which is true. Not because the science failed, but because the object moved faster than our methods could adapt, and the questions it raised require observations we did not have time to schedule. That is the condition of this work. Not certainty, not proof. Just the slow accumulation of constraints, the patient ruling out of possibilities, and the quiet acknowledgement that some visitors leave before we learn to ask the right questions.